Hello and welcome back to the course. We are going to talk about three circuit applications of diodes. The first one is signal rectifier, diode gates, and the last one is diode clamps. There are occasions when you use a diode to make a waveform of one polarity only. If the input waveform isn't a sine wave, you usually don't think of it as a rectification in the sense of a power supply. For instance, you might want a train of pulses corresponding to the rising edge of a square wave. The easiest way is to rectify the differentiated wave like in figure here. Always keep in mind the 0.6 volts approximately forward drop of the diode. This circuit, for instance, gives no output for square waves smaller than 0.6 volts peak to peak. And the reason is because if the input square wave is less than 0.6 volts peak to peak, this diode won't reach the conducting point, which is the forward diode drop, so it will block all the current trying to pass through it. If this is a problem, there are various tricks to circumvent this limitation. One possibility is to use hot carrier diodes like Schottky diodes with a forward drop of about 0.25 volts. Before showing you another possible solution, I want to explain why the signal looks like this here. As you know, a capacitor will never conduct DC current, right? You can try in the simulator to build a DC power source in series with a capacitor, and you will see that current will not flow through it. What you have to keep in mind is that capacitor only conducts DC current until it charges up, and these spikes here are the signals that made through the capacitor until it charged up. And the reason why we have positive and negative spikes is because this square wave, when it's high, let's say it is at 5 volts, and when it is low, it is minus 5 volts. So the 0 volt should be in the middle. The output will contain only the positive spikes because that's the only time when the diode is forward biased, but of course, as you can see, the positive spike got a little smaller due to the forward drop of 0.6 volts. A possible circuit solution to this problem of finite diode drop is shown in this figure here. In this circuit, diode D1 compensates D2's forward drop by providing 0.6 volts of bias to hold D2 at the threshold of conduction. Using a diode like this to provide the bias has several advantages. The first one is that there is nothing to adjust. The second one is that the compensation will be nearly perfect and changes of the forward drop will be compensated properly. Later we will see other instances of matched pair compensation of forward drops in diodes, transistors and FETs. It is a simple and powerful trick. Another application of diodes, which we will recognize later under the general heading of logic, is to pass the higher of two voltages without affecting the lower. A good example is battery backup, a method of keeping something running, for example, the real-time clock chip in a computer, which keeps a running count of date and time, right? That must be continue running even when the device is switched off. This figure here shows a circuit that does the job. The battery does nothing until the plus 5 volts power is switched off. Then it takes over without interruption. So again, when the computer is running, the real-time clock chip gets the power from this 5 volts power supply. Diode D1 will not conduct because its cathode is at plus 5 volts, so this 3 volt is not enough for the diode to make it conduct. After the computer is switched off, diode D1 starts conducting. Alright, I hope you understood. Now let's move to the next one. Sometimes it is desirable to limit the range of a signal, for example to prevent it from exceeding certain voltage limits somewhere in a circuit. The circuit shown here will accomplish this. The diode prevents the output from exceeding about plus 5.6 volts with no effect on voltage less than that. The only limitation is that the input must not go so negative that the reverse breakdown voltage of the diode is exceeded. For example, for a 4148 diode, its reverse breakdown voltage is at minus 75 volts. This resistor limits the diode current during clamping action. However, a side effect is that it adds 1 kilo ohm of series resistance to the signal, so its value is a compromise between maintaining a desirable low source Thevenin resistance and a desirable low clamping current. Diode clamps are standard equipment on all inputs in contemporary CMOS digital logic. Without them, the delicate input circuits are easily destroyed by static electricity discharges during handling.